Okay, so the R square value would be 0 if we performed a regression analysis in this case, because there's no discernible pattern. All the observations are scattered around completely randomly, and you can see the regression line is quite flat. So we would have an R square value here of 0. In the other case here, it appears that there is some linear pattern between the x and y variables, right? So the explanatory variables do explain something in regards to the response variable. So in this, in the case of the Manchester houses, we would say that the size of the houses does have some influence on the pricing of the houses, right? So that's the first assumption that we would check when we do a regression analysis. Then we would also like to check that the residuals are normally distributed with a mean of 0. What we do here is that we I'll just open up FreeStat here, and then you can see if we did a linear regression. In this case, you have a multiple linear regression. So you can have a look at predicted versus actual here and see if there appears to be a linear relationship between these two. So we don't have an actual XY plot when we have a multiple linear regression, because we have more than one explanatory variable. Then if we look at the normal quantile plot, then in this plot we are able to see if the residuals are actually normally distributed. We would like the residuals to lie very close to this line here, to the straight line here. It appears that there's a small deviance from the line in this area. It does not matter in the end if the residuals stray from the line. That's quite normal. That doesn't worry us. What really would worry us was if there was breaks in the middle here, or if there's great deviations from this straight line. In this case, I think we would say that there was no problem in regards to the residuals. There's maybe a little deviance here. We could report that, but otherwise we wouldn't comment further on that. So in order to check if the residuals are normally distributed, we have a look at this normal quantile plot, right? And you can just copy that into your report when you do a regression analysis. You should remember that it's easier either to copy it directly as a picture or to copy from FreeStat into another Excel program and then recopy from there. Otherwise, it thinks a lot about it, your computer. When you're on a MacBook, I don't think it's a problem on Windows, by the way. Okay, then we also have another assumption here, that the residuals must have a constant variance. This means that if the explanatory variable changes, then the residuals, the variance in the residuals should not change. I'll just see, I have a picture somewhere. There's a picture in the FreeStat book somewhere. Ah, there it was. So in this figure 67 on page 188, you can see it appears, this is a residual plot. So it appears that when the explanatory variable changes, then the residuals stay within certain bounds here. They do not appear to show a cone-shaped pattern. In this case here, it appears more that there's a cone-shaped pattern, meaning that there's small changes here, and then further on the changes becomes wider. So we have to watch out for a cone shape here. I don't think these are the world's best figures, because actually some of the points are identical, but that's the idea. I will show you later how we can see this pattern also. But do you understand the idea? If in this case, when you have an explanatory value that is high, then maybe your variance in the residuals is high, and here it stays more or less constant. So constant variance, that's also an assumption, and we talk about, we call it homoscedasticity, and we would like to check for homoscedasticity, we would like the figure to have constant variance, which is the same as homoscedasticity. If it do not have constant variance, then we talk about heteroscedasticity. So these are funny words. I will, maybe to the exam, I can ask you many times what the words are. No, that's just, it's very difficult to pronounce. So it's just fine if you say they have constant variance, right? Okay, then also we would like you can see, I just go back to the assumptions again. These are on page 191. We would also like the residuals to show, to be independent of each other, meaning that there should be no specific pattern in them. I think I will run down and fetch my marker. I'll be back very quickly, okay? Okay, so first I talked about the normal distribution. So if we had the straight line, we would like the residuals to lie something like this very narrowly in here, and it does not matter if they're straight here, right? Also, we should report that we would be worried in regards to this normal distribution assumption if there was some sort of break here. If maybe they did like this. So you can see there's sort of a break in the middle, and in the ends it doesn't matter if they stray a little, right? Just a few points that stray in the ends. And also we could be worried if, for instance, the normal quantile plot had a huge deviation like here from the straight line. Actually, what we do is that usually we just run the regression anyway. We don't look at any ways to go about these assumptions, breaks of these assumptions. So you'll just report that it appears that the residuals are not normally distributed, right? So that was the second assumption. The third assumption with a constant variance. For instance, if you have a scatter plot, what you would look at in Freestat is this residual by a predicted plot. Maybe it appears that there's a little problem here in regards to the constant variance assumption. Can you see it's like the variance here is more narrow than the variance when the predicted value increases? Can you see that? We would like maybe to have more points here also. Do you understand that there's sort of a cone shape here? Okay, so you look at the residual by predicted plot and assesses whether there appears to be a cone shape. So we don't like a cone shape, then we have problems with heteroscedasticity, right? Also, the cone shape doesn't necessarily have to go this way. It could also have been like it had this shape. So we would like the residuals to have even variance, right? Something like that. Yes, and then the residuals, they should be independent of each other. For instance, we should report it in our analysis if if there appeared to be, like if we had some residuals here, and then high residuals was maybe after the high residuals we had low residuals, high, or something, some specific pattern. We would like the residuals to be completely random instead. Yes. So we have to watch out for these four assumptions. If we are looking at doing an analysis with multiple regression, then we should also look for multicollinearity. That means that we should check if the different explanatory variables was covariance together, if they had a high degree of correlation. And I think that it's difficult to say when there's actually multicollinearity. That's difficult to check. So what we usually do is that we do a correlation analysis, and if it appears that two variables have a high correlation coefficient, meaning that if the correlation coefficient ρ is greater than 0.7, or ρ, that's what we call the correlation coefficient with the Greek letter. It's not really necessary that we know this, but it's nice if you write it. So if ρ is above 0.7 or below minus 0.7, then we should also report in our analysis that maybe we have a problem with multicollinearity. We don't have any tools to check specifically for multicollinearity between many of the explanatory variables. That's not part of this course, so we will not discuss that. And we don't have any tools to cope with multicollinearity. So all we will do is that we can report if the correlation coefficients are numerically very high, meaning that they are below minus 0.7 or above 0.7, right? So if we just have a look here, we have these. This, of course, is the response variable, and then we have all these explanatory variables. So in this case, if we would like to check for multicollinearity, we could take all the explanatory variables here. There are 6 explanatory variables. I can then copy these into, where should I copy them to check for correlation? Do you know that? Where can I calculate the correlation coefficient of many variables? I can do that in core M, the correlation matrix, right? I have the correlation between 2 variables here and between many variables here, so I just put them into core M. So here I have the previous analysis, so I'll just delete these, and then I can put in my new variables. So in this case, does it appear? Maybe I won't ask you that because I have something similar in the quiz. But you know what to check for, right? High positive correlation coefficients and low negative correlation coefficients. That's our rule of thumb. If you have the correlation coefficients below minus 0.7 or above 0.7, then we should report them in the analysis report. I know this, when we do linear regression, it's more fun to do the analysis than to check these assumptions, but we just have to check them. Also in our mind map, I have put in these assumptions. So I have changed the mind map a little bit. You can see here, when we do a linear regression, then we check linearity. That's the first assumption of the XY plot, meaning that you check, if you have simple linear regression, you check if it appears that there's some sort of linear relationship between the X and the Y variable, right? The X and the Y variable. And that's the first assumption. This is a very bad pen. It's too good. And then we have the second assumption here, normality of the residuals, where we look at the normal quantile plot if it appears that the residuals stay close to the line. And then we have the variance homogeneity residual plot, where we check if there's a cone shape. There must not be a cone shape of the residuals, right? So then we have to report it. That's the third assumption. And then there's independence in the residual plot. Actually, this fourth assumption regarding simple linear regression is quite difficult to check, but still try to see if you can see if there's some pattern in the residual plot, and then report that if there is. And then if we do multiple linear regression, then we have also this fifth assumption regarding multicollinearity that we should also check. So you can see the 5 assumptions here, there in the mind map, and that's uploaded also. Can you find it? Very good. Okay, so now I covered all the assumptions. Then we try to take the little quiz. Is that fine? So this is actually called linear regression assumptions. So this covers the topics we just discussed. That's strange, it doesn't load. Now load. Okay, I started now. Is that fine? Remember to talk in English? Yes, yes. So you remember how to get in with the pin code. I had some difficulties the other day with being able to start. I hope there's no problem. The lights up. I think this will be an excellent day. What time do you get off today? 3 o'clock? Who's not in yet?
Yeah. Jeg var ved for et fly, fordi min kæreste altid er overforsigtig, når vi går på efter, altså når vi kører ned af de der biler der, så han står altid og hiver jo, nej, stop, og så når vi kører ned.
Oh, everyone's in there.
Så kom du kørende, hele fast der og kører ned.
Where are all the guys today that are usually here?
Yeah, sleeping.
Sleeping?
Yeah.
Okay, it's started. Very good. So actually we look at the observed response and then we deduct the predicted response in order to calculate the residual. I'm impressed. You have plenty of time to calculate. Yeah, I found out, I don't know why I didn't notice this before, ratio image. Every time I try to find the image on the computer, but I can just press this button in order to show the previous image. So that's a bit funny that I didn't see this button before. It's not like it's very cluttered. There's like 6 buttons and I didn't notice that one before. But now I know. Okay, so what I said before was that it was actual. In the case from the exam, you had the prices of Manchester houses, and these were the actual prices. These were the price signs on the houses. But then we made a model based on all the prices that predicted the prices of the houses. So this is the predicted price when we had exactly the number of square feet that was significant for this house, right? So in our case, we would then have that the difference here is observed minus predicted, and of course down here you can see that it's 242 minus 197, meaning that we end up with 45. But that's very good. So in the residual plot here, the question was residuals above 0 would mean that the observed value is greater than the expected value. And since that is how we calculate the residuals, then this must be true. So actually all the values above this line here, this is still the case with the houses. So these are the predicted prices in thousands of British pounds, right? So all the dots up here are prices where the observed value was greater than the expected or predicted value. I could also have written predicted here, right? Expected or predicted, as expected by our model, right? So, for instance, if I look at this dot, then maybe we have something like 165,000 maybe. So our model predicted that this house would cost 165,000 British pounds, but the actual price we can see was then plus maybe 55,000, right? Because this is the residual in thousands of pounds. So in our case here, the house was actually priced much higher than our model would predict. So it was something like 220,000. The price on the house was 220,000, and our model predicted that the house would only cost 165,000. So of course these values, like this value down here, this apparently is a very cheap house compared to what our model predicts. So it must be a big house at a low price, right? Do you understand? Okay. Yeah, these are the assumptions in regards to doing linear regression analysis. Check the XY linearity, and then we check if residuals are normally distributed, independent, and has constant variance. So this is assumption 1, 2, 3, 4, right? Ah, very good. Yeah, maybe the name says everything, I don't know. Outlier. I'm sorry about this. I have to change that one, 2, 6. but no one picked that one. Okay, so there seems to be a decreasing degree of variance. Let's have a look with our new feature, reshow image. Let's have a look. Oh, yeah, that's. Oh, yeah, some of them are a bit short. It's just so you don't fall asleep. Sorry. There seems to be a decreasing degree of variance. Decreasing degree of variance would mean that we would see some sort of pattern like this. But that's not the case, right? And not increasing either, I think. I think it's rather constant. But what seems to what we can see here is that there appears to be an outlier there, right? By the way, if you find an outlier, then if you have a model where you have many possible explanatory variables that you did not use yet, then maybe it can help to include some of the explanatory variables in your analysis. Then maybe you can get rid of outliers. It could also be a measurement error. Then it's also a possibility to exclude the actual observation, but that's not really part of the course either. But anyway, for instance, if you have a data set like on CBS, we had a data set with Peugeot cars, and then there was 3,000 different prices on the Peugeot cars, and it appeared that in the residual plots there was some outliers every time. And when you went in and examined the outliers, you could see that was because they were a special motor that was more expensive than usual cars. So what you could do then was to include a dummy variable or a variable for each different type of model. So you had dummy variables for each type of model, and then you would get rid of these residuals. These outliers. You would not get rid of the residuals, of course, you would get rid of the outliers, right? They would then be included in the normal sky of residual points. Yes. Homoscedasticity and homogeneity, that's the same. So homogeneity of variance means that the residuals has constant variance, and this also means that they have constant variance. And heteroscedasticity, that means that the variance has some sort of cone shape, maybe, that it's not constant all the time, right? So if we have a look, you can see maybe that the variance increases as the predicted values increases. Can you see that? Yeah, okay. So that means that there's a heteroscedasticity. Heteroscedasticity. No, I'll ask you to say 10 times in a row at the exam. That could be fun. Yeah, but it's a very difficult word. Heteroscedasticity. Heteroscedasticity.
Hvis vi kommer ind til eksamen, så siger det, så er det bare tørt. Vi siger det bare så.
Yeah, it's a funny word. Okay, this is something we should check for. Also, it's not necessarily that the residual plot will show a cone-shaped shape when there's a heteroscedasticity. Maybe you can see that it has some sort like this. So it has like this funny shape, right? So the variance increases at a certain point here. Ah, you're fast. Ah, very good. Excellent. Ah, the problem was, didn't you see not? Yeah, okay. But it appears that that the residuals seems to be normally distributed, right? So this was false. It says does not appear to be normally distributed, but they do appear to be normally distributed, right? Not that many, 16. 7 questions left.
Camilla!
Oh, this is interesting. What's the problem here? Except that it doesn't show the picture. No, yeah. Okay, good morning. Yeah. You can see in the picture that clearly there's multicollinearity. We should check for multicollinearity in both simple and multiple linear regression. What is multicollinearity? Do you remember that? Multicollinearity, that's a problem when 2 or more explanatory variables are highly correlated together, so they interact together. Then your multiple linear regression model will have a problem. Why is it not possible to have multicollinearity in simple linear regression? How many explanatory variables are in simple linear regression? Yeah, 1. So is it possible to have 2 explanatory variables or more explanatory variables to have a high degree of correlation in simple linear regression? No. Okay, so this was false. Ah, very good. Well, well, I don't know. You know, numerically means that that the row is greater than row. Maybe I should write it like row numeric is greater than 0.7. So it just means that if row is below minus 0.7, right? Row. No, RHO, you can write it in Word like RHO, and then of course in equation editor, backslash RHO. I'll just show you here. You press Shift Alt 7, Shift Alt 7. So this is a row, and we use that letter, that Greek letter we use for to name the correlation coefficient. It's not really important if you know that, but it looks nice if you do a report. In order to make backslash type shift at 7. Does it work? Shift alt 7 not? Yeah, only on Mac. You have on Windows you have a dedicated backslash button. Yeah, use Alt ground or Alt in order to get a backslash. But it should work. Okay, so we just go back. Mills, who's that? You have plenty of time here. I told you to sit closer. Maybe I can. No, that doesn't help. So if we have a look here, you can see it's a bit difficult to see anyway, but you can see here that sales and profits are highly correlated. They show a correlation coefficient of 0.79. But you answered very quickly. The time was not up, was it? No. And these three, they show high degrees of correlation. Sales and market value show a high degree of correlation, and extremely high degree of correlation is profits and market value. I don't know why they're so highly correlated. I don't think necessarily that your market value always shows your profits. Maybe it's more like profit potential, but they're highly correlated. I don't remember. I don't think so. But I'm not sure. Yeah, in Kyle, a cone, right? So over here you can see that the variance appears to be constant, right? In the other case over here on the right, it appears that the variance is cone-shaped, so there's not constant variance here. Here there's constant variance. So here there's homoscedasticity. Yeah, it's a fun word. Yeah, also linearity, but both appear to show some kind of linearity. A breach of these assumptions does not necessarily mean that we cannot use our model, but it means that some of our estimates are not accurate, and our model is more accurate in some areas than others. So, but anyway, we just report the breach of assumptions in our linear regression analysis. We don't do anything more than that. Okay. Who's 1, 2, and 3? No? Okay, so in this case, we can see that there appears, as I said previously, independence is very hard to check. So maybe this is, but anyway, we try to say something here. It appears that low predicted values means that there's some sort of high residual, and in the middle here there's low residuals and then high again. But so the assumption appears to be violated, right? Also, this independence assumption, we look at a lot for dependence in time series data. This is not part of this course, but you can use time series data to predict very precisely some events doing linear regression models where your variables are timed. So you maybe have the sales for each year, and then you can predict future sales or something like that. So that would be time series. Very good. So the normal quantile plot we use to check normality for the residuals, and here it appears that there's some breach of the normality assumptions in regards to the residuals, right? Okay, what I heard someone talking about these out here. Are these outliers? No, that's right. This is an outlier, right? So the question was there appears to be 4 to 5 outliers in the XY plot, but it actually only appears like there's one outlier, right? So this was the last question. Oh, 13, correct. Very good. Okay, so now we turn to a break. Okay. Jo, vi kan tage en efter. Vi har lige nogle opgaver, I skal rode lidt der, og så bagefter kan vi tage en til, hvis I vil. Ja, det er meget hyggeligt.